Yeah, go ahead.
All right. So like I was saying, welcome everyone. We're all so glad that you're here. Glad that we can have a seminar, even though it's extra cold outside this week. So we'll get started right here. First, I'd like to introduce myself and the leadership team of the GSC. My name's Rodney Hurt. I'm one of the co-chairs this year, along with Roshan. We have our publicity experts, Reza, Rajmohan, Tarun, and Rachel. Support team, Anirban and Emmanuel. And then major correspondents from Robert Rucker and Farouk Mistry, Professor Farouk Mistry. So if you ever have any questions about the GSC or in general, concerns, anything like that, feel free to contact any of us. We also like to invite everyone to our weekly team meeting. We're having them Fridays at 4 p.m. via Zoom. If you're interested, please send an email to myself or Roshan or both of us, and we'll get back to you with an invitation. We'd love to see everyone there. You can come with your concerns or ideas of what we can do this semester, next semester. Just come be part of the community. And then next, I'd like to invite everyone to join our graduate student community engage page. It's a good idea. Well, you can scan this barcode, or I'll put this link in the chat in a little bit. But it's a good idea. We're able to use it as a way to make sure that we keep in touch with everyone, keep everyone up to date on GSC events. And it also shows the university and departments that like the GSC is representing graduate students and other members of the community. So it'd be great to see you sign in there. It would help us out a lot, and we could stay in touch better. We also have a GSC Facebook page where we announce events and post pictures and keep in touch with everyone on Facebook too, if you don't want to sign in or if you don't only check the emails. It's also a great place to see what's happening with the graduate student community. And then lastly on here, we have started a YouTube channel for the graduate student community where we put all of our seminars. So this is just a little screenshot of it. These 6 videos are seminars from last semester, from the fall of 2020. Feel free to go there and subscribe. I'll also put this link in the chat in a little bit so that you have an easy access to it. But it's a great way to go back and refresh on old seminars, or if you miss it, you can catch it on our YouTube channel. And then I hope that everyone can join us in the next couple weeks. We have a couple more great seminars coming up. Next week, the topic is on managing liver cirrhosis. And then we have a following week is simulation ontology for ground vehicle design. Both exciting topics. Again, hope everyone will join us. And then today, Dr. Liu, Professor Liu will be talking about physics-informed statistical learning for spatio-temporal data from stochastic convection-diffusion processes. Sorry, stumble a little bit there, but with that, Professor Liu, I'll turn it over to you.
Sure, thank you. Thank you so much for the introduction. So let me share my screen. Do this. Okay. Can you see it?
Yep.
Yep, great, thank you. It's such a great pleasure for me to be here today and share with you some of my ongoing research. And you see, I think it's my turn to give you an introduction to myself. So I'm currently an assistant professor from the Department of Industrial Engineering, University of Arkansas. So we're not that far from each other. It's really cold outside today. I'm sure you're feeling the same. So I'm currently working on the physics-based or physics-informed engineering knowledge-based data-driven methodologies and their applications. So before I joined the department, I was actually in the industry. I spent 5 years with IBM. So I was there as a research scientist. So I spent 2 years there in New York and 3 years in Singapore. So later on in my presentation, you're going to see that most of my research is actually motivated from my previous projects with IBM. And I also serve as an adjunct assistant professor at the National University of Singapore for like 3 years. So that's like my nighttime job. So during the day, I went to the office in IBM's, and after that, I went to the university, and I regularly taught 2 courses during that period of time. Before that, I spent like a year and a half or 4 months on a joint project between Rutgers University, Qatar University, so in Middle East. Before that, I got my degree from IE, from the National University of Singapore. And as you can see here on the far right, my first degree is actually from mechanical engineering. And so that's where I met Dr. Yingtao Liu. So we went to college together. We graduated at the same time. So like a couple of months ago, when I got an email from Dr. Liu, and he asked me whether I'm interested in sharing my research at this event. I was so happy to receive his email. It's such a great pleasure for me to be here today. Okay, so if you look at my background, I think this partially explains why, although I'm in the Department of Industrial Engineering, I'm still very much interested in physics-based or domain knowledge-based data-driven methodologies and their applications. I sort of want to couple things together. Like later on, you're going to see some examples, right? So perhaps I'm not so interested in building black box pure data-driven models, although I did that before. So right now, I'm more interested in to see how we can couple, data-driven methodologies in engineering domain knowledge or solving engineering problems. Right, that's where I come from. Now, this is the overview of today's presentation. I will start with some background objectives of my research. I'll show you some motivating examples. And after that, I'll move on to the main ideas in the approach. Okay, so because we only have perhaps maybe 15 minutes or so, right? And I will not spend too much time on those technical details, but I will spend sufficient time on explaining the ideas and motivations and the main approach that we took to tackle this type of problems. And then after that, I'll briefly show you the main results, like a summary, because I don't have time to show you the proofs and all the derivations, but I will show you the main results. And finally, I believe I can show you some numerical illustrations that illustrates, how we can apply this methodology to solving a real problem, to solve a real problem. Okay, so during this presentation, if you have any technical issues, for example, if you cannot hear me or you have any questions, so please interrupt me. So please let me know. I really appreciate that. I know this is really challenging sometimes when we're not seeing each other, when this is done in a remote way, because on Monday, for example, when I taught a course, and all of a sudden I received an email from my student, and he told me that, hey, Dr. Liu, we have lost your voice for like 5 to 10 minutes. So please let me know if you just cannot hear me or you have any technical issues. So let's move on to the first section, the background. I started working on this problem a couple of years ago when I first joined IBM. So at that time, we had a project with the Singapore government, the National Environmental Agency in Singapore. So that's the EPA in Singapore. So we had a project together to tackle some urban environmental issues. For example, as you can see here, the modeling of urban air quality using statistical methods. So I'm going to move this a little bit, and also the the modeling and prediction of tropical extreme weather events, because Singapore is a tropical country, right? The precipitation, the annual precipitation there is so high, it rains a lot, and it has lots of thunderstorms every year, especially in summer during the monsoon season. So they're very much interested in, developing some data-driven models that can, enable them to make predictions, especially short-term predictions for extreme weather events. And in that project, we also work on the modeling of smoke dispersion or smoke propagation due to the Southeast Asia, wildfires. It's similar to the California wildfires, but the reasons are different. In California wildfires, I think that was most of those wildfires are natural wildfires, but in Southeast Asia, most of the wildfires are caused by agricultural activities. People basically burn those palm oil trees, and that caused some significant environmental issues there in Southeast Asia. So that's what we did at that time. So during that period of time, I realized, and our team realized, that if you look at these problems, right, there are different types of problems. But if you try to extract the physics behind this, problems, essentially we're dealing with spatial-temporal data arising from physical convection-diffusion processes. Right here, Xi, that's for example, that can be the rainfall process, that can be the air pollution process, that can be the smoke propagation process at time t over the spatial domain S, and A here, this is a advection diffusion operator, right? It depends on the wind, the velocity field, the diffusion, and the decay. And here, this F, that's the source term, the forcing term here, and epsilon here, that's just a random noise, right? So this is the governing equation behind most of these natural processes. Of course, I cannot say all the natural processes, they have the same governing equation, but in general, I'm just saying that, in general, this is something that they share in common. But if you look so if this is the case, if you think about how we can tackle this issue, right, how we can model this type of spatial temporal data arising from advection diffusion processes, we can certainly use physics-driven approach. For example, we can set up the physics model, the partial differential equation, we can solve the inverse model, and we can estimate those initial conditions, boundary conditions, parameters, and then we can run the forward simulation. So that's how we can use a physics model to make predictions. And there are certainly lots of advantages for doing so, because physics model is heavily rooted in physics, right? So we can we can clearly explain the outcome generated by the models. We can use the model for control purposes, monitoring purposes, or even planning and what-if analysis. So these are the advantages of using a physics-driven model. But at the same time, we also have some challenges if you're using, pure physics-driven model. For example, it's going to be difficult for us to make real-time predictions due to computational complexity. So many of these physics models, they're computationally intensive. For example, if you want to run a FEA, right? So finite element analysis model. So it's not something you can get the results in a couple of seconds or a couple of minutes. Right? And also, it can also be difficult for us to incorporate heterogeneous streaming sensor observations in real time when we use pure physics-driven model. For example, when we model the extreme weather system, we can use the satellite image, the remote sensing image. So we usually have remote sensing image in every 5 minutes. So that means every 5 minutes, we need to update the results, update the prediction. And sometimes it can be hard for us to just incorporate streaming data into a physics model in real time, right? And for short-term prediction, a pure physics-driven model may not work well due to the uncertainty associated with the model inputs and the uncertainty associated with those modeling parameters. So for this reason, if you look at the statistics community, right, statisticians, they have proposed statistical spatial-temporal models for the modeling of spatial-temporal data arising from physical processes. most of those statistical models are based on the theory of random process. For example, the general idea is that those statistical models, they use some kind of random process. For example, Gaussian process, that's the one which has been most widely used with certain specified joint space-time covariance structure to approximate the data arising from a physical process. There are certain advantages of doing this. For example, statistical models or data-driven models are usually capable of incorporating observations. And like any statistical model, they have certain advantages in terms of quantifying the uncertainty associated with the process, associated with the predictions or the model parameters. And we can usually use a statistical model to do real-time or short-term predictions. So these are some of the advantages that we can enjoy if we use statistical model, right? But nothing is perfect. We also have some challenges if we use statistical model. The first challenge here is that model specification, right? Simply put, a statistical model looks like y equals fx plus e. So we need to specify the f function, that's the mean value function. For a very complicated process, it's going to be hard for us to specify or even guess the structure of the mean value function. And moreover, if we want to build a statistical model, we need to make some assumptions, typically some assumptions about the covariance structure of the data, like how the data are correlated in space and how the data are correlated in time. For a highly dynamic process, it's almost impossible for us to pre-specify the covariance structure, to explain, to guess how the data are correlated in space and time. So we have some modeling, specification challenges there. And also model interpretation can be another issue because statistical model does not have to be, driven by physics. It's driven by data. Very often it's driven by how the data are correlated, right? The correlation driven model. So if we want to apply this model to some real engineering application, sometimes it's hard for us to interpret the model from using the language of domain knowledge, right? And also because the lack of interpretability of those statistical models, it's harder for us to use a pure data-driven model for control, monitoring, or even planning purposes, because it's not driven by causation most of the time. Those models are driven by correlation. So as you can see here, that there's a clear, need or trend that motivates us to combine or integrate physics-driven model and data-driven model. So here I highlight the word convergence. So this is what I'm trying to do, what I'm trying to show you in this presentation. Figure out a way that we can, integrate basic fundamental governing physics into a data-driven model, such that the model can enjoy the benefits from both physics-based driven modeling and data-driven modeling. Okay, so let me show you, more examples to further elaborate my point. So this is another project I've been working with IBM, which is about the modeling of data center heat distribution. So data center DC are the backbone of cloud services. We all know that. It hosts zillions of mobile apps, online transactions, or searches. So every time we use Google, every time we watch a video on YouTube or Netflix, so basically data center are the backbone of supporting those services. But data center consume, right here. But one critical issue here is that data center consumes a tremendous amount of energy. So we all know that. So DC in the US, for example, consumed 73 billion kilowatt electricity last year in 2020. That's roughly equivalent to 21 standard 500 megawatt coal powered plants. And 40% of the energy is used for cooling the IT equipment. And also because of this, energy costs make up like 70 to 80% of DC operating expenses. And also DCs emit as much CO2 as the airline industry per year. And that's, to me, when I first saw this, I was a little bit shocked. So the key point here is that there is a need for the critical capability for the online modeling of DC heat distribution. In a sense that if I'm IBM or Amazon, I'm running large-scale data centers, I should be able to, monitor or model the heat distribution in my data center almost in near real time. And the heat distribution in data center is a complex, non-stationary spatial-temporal process governed by thermodynamics laws. Right? If we're able to do this, if I were the operator of a DC of a data center, I would be able to, take some actions to eliminate those overheated or overcooled area through targeted cooling or dynamic server load allocation. Right? So if you look at what people have been done in the industry, so certainly people have tried physics-based numerical simulation models. For example, we can actually build a Navier-Stokes equation coupled with the heat transfer module, something like this. And then we can use the physics approach to simulate the heat distribution from within a data center. And this is what has been done in industry, right? And then based on the simulation, we can identify those overcooled areas and those overheated areas, and then we can take actions to get rid of those areas. As you can see here, this is just like a snapshot of the heat distribution in a data center. Okay, but what are the challenges? The challenges are computationally, as you can imagine, it's intensive, right? So it's hard for us to get some real-time prediction results. If you look at this, I put a note on this figure. Full heat maps are needed in every 2 minutes. That means if you want to run this simulation, we have to run some kind of reduced order physics model, right? Low fidelity physics model, such that we can get the results in every 2 minutes. And then we can take real-time actions to control the heat distribution. And model fidelity can be another issue because we know that numerical simulation models will have some error. And uncertainty quantification, that's another challenge if we use a pure physics-based model. So therefore, people in industry, they have also tried data-driven model. Data-driven models approaches might be computationally more efficient. So I use the word might be. They do not necessarily, they are not always computationally efficient, but sometimes they can be. And they do have merit in integrating sensor data streams and quantifying process uncertainty. So this is the advantage of statistical models, right? We want to use the statistics model to quantify process uncertainty. Otherwise, perhaps we don't even need statistics. But the challenge here is that, as I briefly mentioned before, the interpretability can be a problem. Because if the model is purely driven by correlation, it's hard to quantify the relationship between action and consequence. If you imagine, if you're the data center operators, if you want to take some actions, naturally you want to know how's your action is going to affect, the heat distribution in a data center. But this type of question usually cannot be answered by a pure data-driven model. Although the data-driven model can model the heat distribution well, but they usually do not provide us some, the essential actionable insights that operators needed to take actions. So there is there's a need to couple both physics-based approach and data-driven approach for this type of applications. One more example. Here, this is another project I'm working with my students right now. So we're looking at the aircraft UAV collision security evaluation. So basically the goal here is that when we want to understand when a UAV hit the aircraft, so what's going to happen? So that's the simple question. Right. So traditionally or typically, people can use FEA to do this. I still believe that's the right way to do it. Right. But what we want to do here is that we want to see if we can build a data-driven model that can be used to learn the outcome generated from FEA. And then we can use this data-driven model to make predictions for the collision severity, evaluation under different impact conditions. So that's what we want to do. So I have a student, he has very strong background in mechanical engineering, and he has set up these models. We're running FEA models right now. Our goal is that we want to generate, a set of FEA simulation outcomes, and then we want to use statistical models or data-driven models to learn the collision process based on FEA outcomes, and then we can make extrapolations. We can use the statistical model, which is computationally faster to make predictions for other conditions. Because as you can see here, the design space for this type of, or decision space for this type of applications is usually very high. For example, the types of UAV, the location of collisions, the collision height, angle, speed, right? So if you want to use, sometimes if you want to use a pure FEA model to evaluate the collision severity under all these combinations of design parameters, that's going to be time consuming, right? So if we're able to build a data-driven model that can learn from the outcome of the FEA models, and then we can use the data-driven models to make extrapolations. So that's the goal here. So in summary, so the motivation of my research is like this. So we believe that governing physics or domain knowledge impose critical constraints on how data can be modeled and how models should be interpreted. This is, we're talking about engineering applications. We apply data-driven models for engineering applications. We believe this is very often the case. And especially for high-stakes applications that require interpretable models and explainable decisions, and pure data-driven approaches can be limited in generating actionable insights or facilitating the discovery of new engineering knowledge. So, motivated by these two observations, what we're currently doing is that we want to see if we can build physics-informed spatial-temporal models such that the model will have the following advantages. For example, the model should be able to incorporate basic physics such that models are interpretable, and the model should be, handle streaming sensor data such that the model can be used for real-time applications. And of course, because of that, the model needs to be computationally efficient. So we need some computationally efficient algorithm to estimate those unknown model parameters. And if we can achieve these 3 bullet points, and then we can use this model for monitoring, forecasting, and we can use this model to solve some inverse problems like source detection problems. So this is the what motivates us for pursuing this research direction. Okay.
Dr. Liu?
Yes. Is there a question? Yes.
I have a question. Can you hear me?
Yeah. Yes, I can.
So you talked about the interpretability for data-driven models.
Mm-hmm.
So generally, the neural networks, which are more powerful as they can approximate any nonlinear function, they are considered as a black box models.
Yeah.
But coming to some other machine learning models like the simple linear regression and then the decision trees, they can be considered as interpretable, right? Or
in a way, yes.
Okay.
Yeah, because I think the interpretability is always in a relative sense, right? For example, if you compare a decision tree to a random forest, probably I would say a random forest is less interpretable than a simple card decision tree. Mm-hmm. But if you compare random forest to a neural network, maybe random forest is more interpretable than a neural network. But my point is not to criticize neural network. I also do neural network. It's more like, what kind of model we want. It's just like for certain applications, maybe it's more, it makes more sense for us to develop more transparent models such that engineers can adopt those models easily. It's just like we can provide different, options or solutions for the users or engineers for different types of applications. Neural network is very, very powerful in terms of describing the data, capturing the nonlinearity in the data. Yeah.
Thank you.
There's always a trade-off, I believe, and this is just a particular angle that we picked to pursue our research. That's all. Okay. So let me move on. So for this slide, perhaps I'm going to skip this slide. I'll move on to the main ideas in approach. A historical perspective. This is like a literature review for the statistical modeling of spatial-temporal data. If you look at the statistical spatial-temporal models, so I would say the mainstream model was proposed in the 90s, and now these days we call that modeling approach the geostatistical paradigm. The idea is like we use a random field, a random process to approximate the spatial-temporal process. For example, the Gaussian process or Gaussian random field, and that's the one which has been widely used for approximating a spatial-temporal process. And because for large data sets, the computational, the Gaussian random field can become computationally expensive because we need to converting the dense matrix, the covariance matrix, over and over a time when we do parameter estimation. And people also propose the dynamical spatial-temporal models. In statistics, people call this dynamical spatial-temporal models, but it's just space model. And over the past couple of years, I've seen lots of research focusing on the integration of physics and spatial-temporal models. So we call that physics-informed spatial-temporal models. So the first category of this approach is what we call the non-intrusive approach. For example, we could incorporate Bayesian priors, regularizations, or even hard constraints to the data-driven model, such that we can force the data-driven model to satisfy certain, physical constraints, right? And we can also use statistical models as a bias correction here. That's like the uncertainty quantification. And I've also seen people use different, objective functions to strike a balance between data-driven learning and discovery of physics, right? Like recently, I think over the past 3 years, people have proposed physics-informed neural network, PINN. So PINN basically has an objective function that strikes a balance between data approximation and also the physics constraints. And the last approach is people try to explain the outcome of machine learning models, and that's what we call the explainable machine learning. So in this research, we want to try a slightly different approach. We want to make this integration more intrusive. I mean, we want to come up with a way that enables us to integrate physics into spatial-temporal models in a more intrusive manner. Right? So in other words, if you can look at the statement at the very bottom of the slides, we want to embed data-driven models into the solution manifold of governing physics. At least we want to make sure that the output of the statistical model is not far away from the solution generated from governing physics. All right, so we're going to call this a structure exploiting and preserving approach, SEP. Okay, so let me briefly talk about the idea. So this is just like a very general overview to the idea. And there are lots of technical details here, and probably I won't go into this technical details. Suppose that here we have data arising from a process that looks like this. Right? This is the governing process, which is nothing but a partial differential equation in convection-diffusion process. Here, A, that's the convection-diffusion operator. So F, that's the forcing term. And here we add a noise term to it to make it this a stochastic partial differential equation. Traditionally, so when people try to model data arising from this type of process, people use random fields with a certain space-time covariance structure to approximate data arising from such process. So in this approach, this is what we have been trying. We first, perform a space-time decomposition of the process. So in other words, we project the process from the space-time domain to a spectral space, which is spanned by a spatial basis function. So this is a very, I think we're familiar with this type of approach, right? For example, we can think about the proper orthogonal decomposition, which is a technique that has been widely used for building reduced order physics models. You can think about Fourier transforms, so that falls into this category too. Right, so if we do this, as you can see here, F, that's the spatial basis functions spanning the spectrum space. And here, alpha, that's the coefficient. If we use Fourier transform, alpha is the Fourier mode, right? So alpha in general, we're going to call that coefficients. So here, because we're dealing with a spatial temporal process, so alpha needs to evolve over time. And now we want to use a stochastic process, which is characterized by a stochastic differential equation here to characterize the dynamics of this alpha. So as you can see here, if you look at this space-time decomposition, so the f, the basis function is fixed, right? So once it's fixed, then it's determined, it's fixed. And the alpha, it changes over time. So, and then we want to capture the dynamics. We want to describe how this alpha evolves over time using some stochastic process, which is characterized by an SDE. So I'm going to come back to this later. For this spatial basis function, for example, we can use POD, proper orthogonal decomposition. We can use Fourier basis. So if we use PAD, we need to learn basis function from data. If we use Fourier basis, then it's basically fixed, right? It's determined. How about the stochastic process of alpha? We want this structure of this G, the stochastic process, to be determined by the governing physics. This may or may not be possible, but at least that's the goal here. That means we want to use this physics to determine the structure of this stochastic process of alpha. In a sense that if we do know that the data is, the data arises from this particular governing equation, and then after this space-time decomposition, the dynamics of alpha has to be modeled by a SDE with a certain structure. So we want this structure to be determined by the governing physics. As I said, this may or may not be possible, but if this is possible, then it provides us an opportunity to embed the basic physics into the statistical model that we're going to build later. And for example, I'll give you some examples. For example, these are just two examples of how we can construct this SDE. The first one is a linear model with the drift, okay? It's a simple one. The second one is a polynomial stochastic differential equation. And of course, these are just two examples. But the key point here is that we hope we can, the structure of this SDE is determined or at least motivated from this governing equation. So what are the advantages of doing so? There are a few advantages of doing this from the statistical modeling point of view. Since the basis functions are fixed, whether it's learned from data if we use POD, or it's given if we use Fourier basis, right? The modeling of the spatial-temporal process, which is a process over space and time, can be converted to the modeling of the multivariate stochastic process alpha. Because of the space-time decomposition or approximation, once we know alpha, then through this linear operation, we can find psi. That's the space-time process. Right, so this is the modeling advantage that we have. The first modeling advantage that we have, we can make things mathematically more tractable because the modeling of this multivariate stochastic process alpha is expected to be easier than the modeling of the space-time process. And the second advantage here is now the dynamics of alpha, this SDE, the structure of this SDE can be established from physics, right? This may or may not be possible, but once if this is possible, then we have the chance to directly embed physics into our model. And the third advantage here is that once the dynamics of alpha has been established, it is possible to find the space-time covariance structure of the original space-time process. You can easily see this because if we know this structure of this stochastic process, this SDE, we know the temporal correlation structure of this alpha. If we know how alpha is correlated over time, since the original space-time process, psi, can be obtained from alpha through a linear operation, then we can easily obtain the space-time covariance structure of the original process. If you still remember that traditionally when we use a random field to approximate this original space-time process, one of the challenges is it's hard for us to specify the covariance structure to specify how the data are correlated in space and time for this original space-time covariance. But here we sort of bypass that issue. instead of directly working on the covariance structure of the original space-time process, we work on the SDE. So once we know the temporal covariance structure of alpha, through this linear operation, this decomposition, we can immediately obtain the space-time covariance structure of cosine. This is important from the perspective of statistical modeling, because we want to build a statistical model, we need to characterize how data are correlated in space and time. The next issue is that we can do dimension reduction by keeping the low frequency terms. We may or may not need this, but just in case we need to do that, we can do it. And the last bullet point is that we're able to, once we have established this theoretical framework, we're able to embed the model into a hierarchical dynamical spatial-temporal model, which have been well established. We sort of connect our research to the existing methods in the literature. Okay, so this is just like an overview of how we're gonna model the data. So now I'm gonna quickly show you some of the main results. Right? As I said, I won't go into those technical details, but if you're interested, you can always refer to our paper. Right? So let me use this image as an example. So this is a radar image of the weather system. You can see we got this data from Singapore. So this is the island of Singapore. You can see the weather system, right? This is basically the rainfall process. And if we perform, I just want to zoom in. I just need, for this illustrative example, I just want to take a look at this region. So I'll make it bigger. So this is how the original radar image looks like. It's on an 80 to 80 by 80 pixel array, right? So the distance between 2 pixels is about 500 meters. So that's the resolution of this image. So this is how it looks like in the original space-time domain. But we can perform, for example, a decomposition. For example, we use Fourier transform. We don't have to, but let's say we use Fourier transform. We can perform a 2D, discrete Fourier transform, and then we're going to have the real part and the imaginary part of the coefficients. So that's alpha C and alpha S. So usually we all know that for a process like this, the energy is concentrated in the low frequency region. So we can sort of get rid of the high frequency area if we have to do that in exchange for some computational advantage here. So this is just like a zoom in image of the first one. If you look at the scale, this one, the wave number goes from -39 to 40. In this case, the wave number goes from -7 to 8. Okay. So this is just the low frequency part. You can see that later on, if you want to build a model, we can just focus on this part. So what's the idea? The idea here is that instead of modeling the original process in space and time domain, which is shown on the far left side, what we could do is that we could try to model the dynamics of alpha, which is the real part of the Fourier mode and the imaginary part of the Fourier mode in this case. Right? And we want this dynamics of the real part of the Fourier mode and the dynamics of the imaginary part of the Fourier mode be determined by this governing physics. Right? So that if we can do that, we're able to inject or embed the basic physics into our data vision model. So let's take a look at this, how we can get this done. So the first step is that we perform this Fourier transformation, the space-time decomposition. So we're going to express this, approximate the process in space and time by a linear combination of basis function. You can imagine Fourier functions and a multivariate temporal stochastic process alpha. Okay, so this is the space-time decomposition. That's the first step. And then, as I've already explained this, so if we can do this, since F is fixed, all we need to do is to figure out how we can model alpha. If we can model alpha, we can model this cosine, the original process in space and time. And alpha is the multivariate stochastic process, right? The multivariate stochastic process. Now, at this point, we have two options. The first option is that we can just learn alpha using pure data-driven approaches. For example, we can use neural network to do that. We can use vector autoregression to do that. That's not a problem. Or if we want to integrate physics into our data-driven model, then we want the physics, SPDE, to determine the structure, the dynamics, the temporal evolution of this alpha. Right? So we took the second approach. If we took the second approach, then we have some natural questions. The first question is, what is the dynamics of alpha if the underlying process is governed by this SPDE? That means our data comes from this governing equation. If that's the case, what's the dynamics? What's the temporal evolution of alpha should be? Right? That's the first question. We can ask a sub-question: what is the dynamics of alpha for real value processes under discrete sampling? Because for many engineering applications, we're dealing with real value process under discrete sampling. And the second question is, what's the covariance structure of the original process in space and time? So we need to answer this question if we want to build a statistical model, right? That means we need to figure out what's the temporal covariance structure of alpha. If we know the temporal covariance structure of alpha, through this linear operation, we can figure out the space-time covariance structure of psi. The next one is, once we have established all this, how do we embed the results into an existing framework, which is called the DSTM, Dynamical Spatial Temporal Modeling Framework. And the last question is, how do we perform efficient statistical inference? So these are the main questions that we have answered in our preliminary work. So I'm going to quickly show you the main results. The first results, the dynamics of if the underlying process is governed by this governing equation. What we can do here is that we can perform the decomposition here, and then we substitute this decomposition into the original partial differential equation, and then we perform the well-known Galeckian projection. We're able to get this proposition. So I'm not going to the details, but if you look at the proposition here, you can see a stochastic differential equation. So this is the equation that characterizes the temporal evolution of this alpha. That means if we know this equation, we know how this alpha should evolve over time if our data does come from this partial differential governing equation, which is shown above. And this G here, that's a matrix operator, and the elements, the components of this G can be computed by this equation. So once we have this SDE, we sort of know how alpha will evolve over time based on this governing equation. Right? So if you look at the literature, so similar results were obtained a couple of years ago, but in that paper, the authors, they assumed that the convection-diffusion does not change over time. So in our work, we sort of relax this assumption. We allow the convection-diffusion operator to change over space. In a sense that if you imagine the propagation of smoke, right, the wind vector might change over space, right? The wind speed, wind direction typically vary over space. And the difference from the statistical modeling point of view here is that when the convection-diffusion operator does not change over time and space, then the evolution of multiple Fourier modes are independent, are decoupled. But in our case, in other words, the G is a diagonal matrix in that case. But in our work, we consider spatially varying convection diffusion. Then the G is no longer a diagonal matrix. The G is a dense matrix. That means the evolution of this multiple Fourier modes, alpha, the different components of alpha, they're coupled with each other, sort of. If we try to come up with a interpretation from physics, this can be explained. This is usually known as the nonlinear energy transfer between multiple scales, between different Fourier modes, because they're all coupled with each other. So this proposition basically answers the question: if our data arise from a partial differential equation looks like that, and then the evolution of alpha has to be determined by this stochastic differential equation. And then we're going to embed this into our statistical model. And then the second question is, what's the temporal covariance structure of this psi, the original process? And this is what we can do. So in order to answer this question, all we need to answer is the temporal covariance structure of alpha. And through this linear operation, we can get a space-time covariance matrix of the original space-time process, psi. And this is given in the second proposition of our paper. I'm going to quickly go through the slides. And this one is the proposition that basically shows the dynamics of alpha for a real value process under discrete sampling, because we believe this is a very important case for engineering applications, because we're dealing with the real value process under discrete sampling. And this proposition establishes the connection between our model and the existing statistical modeling approach, which is called the IDE-based model. So one important modeling approach in statistics is to capture the spatial-temporal dynamics using stochastic integral difference equation IDE. So we can show that our model, although it's motivated from a different angle, but we can still prove that, we can still show that our model has a natural connection to those existing IDE-based model. If you look at this expression, you can clearly see that the space-time process at the next time step can be generated by a weighted, combination average, a linear combination of the process at the current time step. So this is what we call the IDE-based representation. And after this, we can combine our theoretical results into a DSTM model, which is nothing but a state-space model. If you look at the first one, the observation equation, so that is motivated by the spectrum decomposition. So Y, that's the data. The theta here, that's the Fourier coefficients. And the second equation is obtained from our propositions 1 and propositions 2 that captures how the alpha is part of theta, it evolved over time. So at least you can imagine that we're able to build this state-space model. And after that, we can solve the space model using Kalman filter. I think this is something that you guys are familiar with. So I'm going to quickly fast forward to this part, numerical illustration. I think I'm running out of time a little bit. I hope I can get this part done in 5 minutes. And so I'm going to show you some numerical examples. So I'm going to use this short-term precipitation nowcasting as an example. So what you see here is a weather radar, an extreme weather event. You can see here, this is the spatial domain is about 10,000 square kilometers. So this is the basically the coverage of the radar image. It's 200 by 200, has 200 by 200 pixel arrays in it. And this radar image is taken from 1 kilometer above the mean sea level. So that's the typical height that people look at. And here you can clearly see that there's a weather system moving from the west side of the spatial domain to the east side of the spatial domain, right? It's just a rainfall process. And here you can see we perform the Fourier transform for each image. You barely see anything. That's because the energy is highly concentrated on the in the low frequency part. You can actually see something at the center of these two images. This actually justifies why we can do dimension reduction by throwing away this high frequency component. Okay, so if that's the case, let's just do the dimension reduction. We don't have to do this, but I just want to use this as an illustration. Suppose we perform the low pass filtering by keeping only the low frequency terms. As you can see here, instead of working on the original images, we can work on the low pass filter images. So that we can achieve a much faster, computation. Now, this figure shows you basically the modeling results. Suppose we have the data and we run the state-space model that we built. And what you see here is the original image, the actual data on the left side, the low pass filtering image. And on the right, what you can see here, that's the filter data generated by our state-space model using the Kalman filter method, right? So you can see two things. One is that the method can estimate the wind field. You can see those white arrows. Those white arrows indicate the wind field. You can see the wind direction and wind speed gradually vary over space. And usually we don't know this, but using this model, we can estimate the wind field. That's the velocity field. And then we can also get the filter image. So they match pretty well, and they should, right? It's just a filter problem. And after that, you should remember in our partial differential equation, we have the source term. This model can also help us estimate the source term. The source term in the context of this problem refers to the growth and decay of the rainfall cells. Because we apply this method to tropical area thunderstorm. For tropical area thunderstorm, the strength, the intensity of rainfall can grow, can decay, can in a very short period of time. So therefore, it makes sense for us to use this model to capture the source and decay of the rainfall process. And what you can see here is that the first row shows you the actual data, and the second row shows you the estimated source and decay of the rainfall intensity. So the red area indicates the area where the rainfall intensity is growing, and the blue area are those areas where the rainfall intensity is decreasing, right? And once we have all this information, once we know the source and decay, the wind velocity, the diffusion, and now we can make predictions, right? And I'm gonna show you the prediction results like this. What you can see here is that the figure on the left side that shows you the actual data, right? We're making 5 minutes to 25 minutes ahead prediction. For tropical area, that's typically the case. For example, in Singapore, people are interested in 15 to 45 minutes lead time, weather short time nowcasting. All right, so this figure on the left side, this animation shows you the actual process, and the one on the right side shows you the predicted process. We can clearly see a few things, right? When the prediction horizon grows, the prediction performance drops. This is sort of expected. And the main reason is because we believe that's because the change of wind field, the wind direction and wind speed over the following couple of 30 minutes to 45 minutes. If the wind direction changes, then there's no way for us to actually predict the dynamics, the motion of the weather system. But in general, I believe this model can capture the dynamics of the weather system and makes reasonably good predictions for this type of applications. Now, we do a comparison between the proposed method and the other two methods, which are commonly used by the Meteorological Society. We look at the mean squared error of the precipitation nowcasting in terms of millimeter per hour. That's the rainfall precipitation. We look at 5 minutes ahead prediction, 10-minute ahead prediction, all the way to 30 minutes ahead prediction. And now if you look at the MSE values generated by different models, you can clearly see that I think our model has the best performance, at least for this 199, almost 200 thunderstorms data collected from 2 years. So we had the data from 2010 and 2011. So we tested the model based on these 199 storms within 2 years. And it looks like in terms of MSE, our model can provide the best performance here, the most accurate prediction. So here I put 2 bullet points here as a summary. So both accuracy and interpretability can be simultaneously improved by integrating governing physics into data-driven models. Under the proposed framework, this is exactly what we want to achieve. And this conclusion is consistent with a recent claim. So there was a paper published on Harvard Data Science Review by Professor Rudin and Radin. And in that paper, they made a claim that a belief that accuracy must be sacrificed for interpretability is inaccurate. So we totally agree with that judgment, because as you can see here in our experiment, we can clearly see that for many engineering problems, if we're able to integrate physics into data-driven models, we don't have to make that sacrifice, that compromise, right? We can improve both accuracy and interpretability of the model at the same time for engineering applications in a domain knowledge intensive environment. Okay, now here comes the very last slide. So in this research, we're still working on this, and I believe I'm gonna keep working on this for years. So this ongoing research has created and validated a structure exploiting and preserving spatial-temporal statistical learning framework that enables the intrusive integration of governing physics or engineering principles into data-driven models. And these are my collaborators. They're my former colleagues from IBM, where I'm still working with them on this problem. And the preliminary results has been accepted by JASA, Journal of the American Statistical Association. The paper is already available online. It will be published, printed, I guess, maybe at the end of this year. I put the archive paper there. And if you're interested in this work, I also put my code on GitHub. So if you're interested, you can certainly take a look, or you can ask me questions. So it will be my pleasure to have more discussions with you after this. So I guess this is the end of my presentation. Yeah, thank you. Thank you so much for attending the talk. Thank you. Any questions?
Thank you, Xiao. I really appreciate your presentation. I
Yeah,
have
thank you.
I have some questions, but I will give the opportunity to our students first, just in case someone want to ask you some questions.
Sure.
Usually for online meeting, I was told we should give audience probably 10 minutes to turn on the microphone. Yeah. Yeah. Okay. Great. Since nobody turned on their microphone, I'll go ahead with my questions. So I really appreciate you give the presentation, and I believe this research area is very popular. And then I can see there's a lot of potential applications. My first question is, I heard you talk about probably there are two approaches. The first one is the data-based model can be integrated into a physics model, or vice versa. So the physics, maybe governing equations, will be used in the pure data model. So in which condition do you think is more appropriate for which case?
I would say this approach has, if it works, I think it should work very well because it's more intrusive. We directly embed physics into data models in one way or another, sort of. But it does have limitations in the sense that we may not always be able to do this. Like, for example, the alpha, we want the structure, the dynamics of alpha to be directly derived from physics, but this is obviously not always possible. This leads to the other modeling approach, which is also very powerful, but less intrusive, non-intrusive. It's like, for example, physics-based, physics-informed neural network. I think that falls into that category. It's like they have two objective functions. The first objective function minimizes the difference between prediction and observation, and the second objective function sort of minimizes the discrepancy between the data and the partial differential equation, the governing equation. So from the learning perspective, I'm sure the non-intrusive method in general has very good performance, especially if you use neural network. That's very powerful. I'm sure I can learn the very nonlinear structure very well. But for this approach, since it's intrusive, if it works, I also expect it should work very well. But the thing is that it does not, it's not always available. And so,
okay.
Yep.